This lecture is vector cross product. So if we have two vectors, u and v, we say that u cross v is equal to, and we'll develop the formula shortly, but the idea behind it is u cross v is another vector. So what does it look like? If you point your fingers of your right hand in the direction of u and curl them in the direction of v, then your thumb is going to point in the direction of the vector u cross v. So it looks like this. It's perpendicular to the plane of these two vectors. So these are on the whiteboard. So u cross v is perpendicular to the whiteboard. All right. And second, the magnitude of the cross product, the magnitude of this vector is equal to, well, what we do is make a little parallelogram, and we say the area of this parallelogram is, well, let's take u cross v and figure out its magnitude. Okay? So that's what the vector looks like. All right, so how do we calculate it? Well, the formula, if we write it in this notation, the first component, the second component, and the third component, is rather lengthy and complicated. In fact, almost no one really memorizes it. What they do to do the computation is a little symbolic trick, and this is how it goes. First, you write the unit vectors I, j, and k. Okay. Next, you write the first vector, in this case u, so that's the components are u1, u2, u3, and then the second vector is v, or v1, v2, v3. So these are indeed vectors, and this first row is not really a vector, or you can think of it as a vector of vectors. This doesn't make a whole lot of sense. So it's not a real 3x3 matrix in the linear algebra sense, but it looks like one, and we use it to get our answer. Now what we're going to do is to take the determinant, and vertical lines are the symbol for taking the determinant. Now, if you don't know how to do a determinant, that's okay. I'm going to show you what you need to know to get the answer, and the answer is to fill in these blanks. So what we do is we expand this 3x3 pseudo matrix across the first row. So we write I, and then we have some information here. And then we write minus j, this is a vector, right? A unit vector. And we have some information here. And then we write plus k, and we have some values here. So let's start with I. We cross out that row and that column, and what we're left with is this 2x2 smaller matrix, and we're going to take the determinant of this 2x2 matrix. By definition is this times this minus this times this. So we write u2 times u3 minus v2 times u3. Okay? And these are just numbers or variables or expressions as functions of x, y, and z. Okay, so we have minus j. So again, we cross out the first row and the second column, and we're left with these four values, 2x2 matrix, or sub-matrix, if you will. And we take the determinant, u1, v3, minus V1 U3. Okay, and then finally cross out first row, third column, we're left with U1 V2 minus V1 U2. Okay, so that's how we figure out the value of the cross product. And you can see it's a vector with components I, J, and K. Now, we like to make this negative a positive, so it's in a more friendly form, so to speak. So what we can simply do is multiply this through the value here. Or in other words, we can turn this to positive as long as we turn this to positive and this to negative. So now we have the components that go up here. The first is U2 V3 minus V2 U3. Okay. The second component is, well, we would typically write it V1 U3 minus U1 V3, and well, let's actually write it. And the third one is just what it says here. Okay, so that's the technique for determining the cross product of two vectors. Now, you should note that U cross V, let's clean up the board a little bit. If you compare U cross V and V cross U, well, they're almost the same. They're the same in magnitude. But when you do V cross U, we're going in the other direction. If this is positive, then this would be negative. So we say they're not really equal. They're equal as long as we make one of them a negative sign. Now that's unlike U dot V and V dot U, which are truly commutative. Cross product, the operation is almost commutative. We call it anti-commutative, I believe. Yeah, anti-commutative. Okay, I want to say one more thing, and then we'll be done. I want to emphasize, if we take U cross V, then we take the magnitude, the length of U cross V, that's equal to the area of the parallelogram. It's very important to understand and remember that fact. Now here's a few more facts. If we had, say, I'll use, I don't know, B, A, so we could do B cross A and take the magnitude, that would give the area. Now if we had a third vector, call it, I don't know, C, and it doesn't have to be straight up, I just happen to draw it that way. Well, if we put the C here also, and here, we kind of connect the dots, what we get is a box, often called a parallelepiped, and much like we have area here, we can determine the volume, and the formula is to do B cross A first. Okay, that'll give you a vector, and then simply dot it with C, and that'll give you a number, and that'll be the value of the volume of the box up to the sign, SIGN. That's because this could be negative. So if we take the absolute value of this number, then we have an equation here that's correct. All right, now you'll see one more formula, typically in books. Instead of doing this, we could simply do A1, B1, C1. Oh, I'm sorry, that's not right. A1, A2, A3, B1, B2, B3, C1, C2, C3, and take its determinant in the normal sense. Okay. That'll also give you the volume up to the sign, SIGN. So all we have to do is take the absolute value of this number, and we have equality. So these are just two formulas for volume. Okay. And this first one's called a triple product, and this one, I'm not sure what the name is, but it is valid. And I want to emphasize this is a vertical bar meaning determinant. This is a vertical bar meaning absolute value. This is not the magnitude of a vector. Okay, so these two vertical bars are not the same as the vertical bars here. Okay, I thought that was important to know. Again, this is really important to understand and to do, especially when we do some of the fundamental theorems of multivariable calculus. You really have to understand what's going on here. This formula is just nice. Not important really to this course. It's important to people that like to figure out, I don't know, volumes of boxes. So that ends this lecture. Thank you very much.